right. Okay, so homework is almost done. I'm almost ready with it. Post it today, I hope. Homework 2. Homework 2 will be due on Sunday, October 9th. So you have plenty of time. It'll be kind of long. I'm making my assignments kind of long this year. So the homework 2 will be due on October 9th, and it will cover this stuff and classical statistical inference, which is what we're going to get into that real quick, but that's like t-tests, STATS 101 type inference. We'll see simulation-based inference, classical inference. We'll learn a little bit about Bayesian inference, and you will learn the basics of linear regression. The homework will cover all of those, due on the 9th, and then the first exam is that Wednesday on the 12th. So I don't have room to extend the due date on this one. We're going to wrap it up, and I'll discuss it on Monday of that week. So Monday the 10th, we'll talk about the exam, and I'll go through homework solutions and answer any questions that you have. What I've been talking about is how do you do statistical inference? Confidence intervals and hypothesis tests. And a modern way to do this is with your computer, like computationally, in particular using simulation, either randomly drawing from a particular distribution, or resampling from an observed data set, or in some cases, directly simulating random numbers from some probability distribution that we think applies. What we've been focusing on right now so far is this thing called the Bootstrap. Let me remember where we ended up last time. We have this script. Yeah, we were looking at this data set, not a biostatistics data set, but sufficient for illustrating what we're doing, where we had win-loss record for a football team over the course of a 16-game season. We observed 9 out of 16 wins. That's our observed data. We have 16 zeros and ones, and there's 9 ones, 7 zeros. We talked last time about how a p-hat, like we have up at the top here, a sample proportion, which is an example of a sample statistic, we talked about how that is a random variable. If we had multiple 16-game seasons from this same team, we would see different estimates of p for them. This season they won 9, the next season they won 7, then they won 8. It'd be randomly varying. So we simulated a whole bunch of 16-game seasons. Simulated 1 million of them, all at once by using the R binom function, which generates random realizations of binomial random variables. If we're flipping a coin essentially 16 times and asking, did it come up heads? As in, did you win in each of these games? If we're running a trial multiple times, 16 times, all the trials are considered independent of each other, and the probability of success on each trial is the same. Under those conditions, we are working with a binomial random variable. So we could use the binomial function in R to just simulate a whole bunch of cases where n is the number of trials that we saw, in this case 16, little n is 16, and we can simulate from a particular choice of p. In this case, we said suppose P is really equal to 0.5. They're really an average team. Simulate 1,000,000 16-game seasons, and let's look at what P hats tend to look like. Okay, so I'll run this again, and what we saw was that if they are an average team, if P is equal to 0.5, then 40% of all 16-game seasons would be expected to have 9 or more wins. And that's just by chance. They are not an above-average team. Long-run proportion of games they should win would be 0.5. But just by chance, when we do 16 trials and count up the number of wins, we will see a variety of win totals. We see a substantial proportion over here, 10 or bigger. There's a substantial proportion over here, 5 or fewer. An inferential assessment of this would be, suppose we wanted to specifically ask, are they an above average team? Yes or no? Then this simulation would allow us to answer that in a probabilistic way. We can't ever answer absolutely in statistics. The only way you can answer or report the value of some parameter is if you have access to the entire population. We would have to watch them play an infinite number of games. So what we can do is say, if it was an average team, how frequently would we see win totals like ours, or even more extreme relative to what we think it should be under the null? So basically, how likely would it be to see win totals out in the tails from this distribution? What we computed specifically over here is what proportion of the time do we see 9 or even more? So we're specifically asking, if that's the way we're going to compute this probability, we're testing null hypothesis, they're an average team, P is 0.5, and alternative hypothesis is one-sided. Because of the way I computed this, we're only assessing how likely would it be to see our amount or even more. We could do what's called a two-sided alternative, in which case we would ask how likely would it be to see a 9 or more, or a 7 or fewer. Both of those are 1 unit away from the null choice of 0.5 or 8 wins. This is a one-sided alternative. This number that we computed via simulation, 0.401617, is the probability we'd see data like ours, or even more indicative of our alternative hypothesis if P is 0.5. So via an inductive line of reasoning, we would conclude that P equal 0.5 is a plausible choice. It's a plausible value for the true value of P. It is consistent with what we saw. It would not be unusual at all to see 9 or more wins out of 16 games if P is 0.5. So because this number, this P value, is big, in particular it's not less than some threshold like 0.05, it's big, so we would say we don't have enough evidence to reject that null hypothesis. Fail to reject. All right. So what we did up above was taking advantage of exploiting the fact that these data, this scenario, is a binomial distribution scenario. What we next saw was a more general way to do the same thing without having to make any statements about distributions, which is attractive, because then you can take this technique and apply it to anything. This technique is the Bootstrap, And we initially used the Bootstrap to compute an interval estimate for our parameter of interest. Our parameter of interest, P, probability they win a randomly selected game. Let's see if we can put together a lower bound and upper bound about which we can say, I'm such and such confident that the truth is inside of it. That's a confidence interval. Here's how we did the Bootstrap. If I go back to the notes briefly, Bootstrap is a pretty simple idea. It, in essence, involves sampling with replacement from an observed sample. By sampling with replacement from our observed sample, we get as many new samples as we want. And it turns out that each of those new samples, even though they didn't involve taking a new sample from the population, even though we're just sampling from our one sample from the population, we can still use them as if they were draws from the population. They have the same operating characteristics. If you then have multiple Bootstrap samples, samples with replacement from your data, you can compute the statistic of interest for each of them. And then you have a pile of statistic values. A pile of statistic values is sufficient to represent the sampling distribution of that statistic. And that's what we need for inference, sampling distribution of our statistic. Bootstrap is a resampling technique that enables you to approximate sampling distributions. Here's what it looked like with the Houston Texans data. We represented our sample of data as in numbers, or zeros and ones in this case. N is 16. I have 9 ones, 7 zeros. The Bootstrap, we do it inside a loop because it is iterative. For each of capital B iterations, I'm doing 1,000. For each one, sample with replacement from our in numbers. So this right here, samples with replacement, that will give me 16 zeros and ones that were drawn with replacement from our original 16 zeros and ones. So that highlighted piece right there is creating a Bootstrap sample. Then we computed with that the statistic that's of interest. Okay. Yes. Sorry? To capital B? What should we choose capital B to be? There's no perfect answer. 1,000. I think it's probably fair to say a few thousand is a good idea generally. There's not like a exact answer to how many you should do. The fewer you do, the more variable the results will be. The more you do, the more stable the results will be. Most of the time, it won't take but a second or two to run, even with a few thousand iterations. But if you have a really big data set, and or if you're having to compute something intense inside each time to get your statistic, it can bog down and take a long time. So just be aware, if you plug in, why don't I do 100,000, you may have to wait hours for the computer to finish, depending on what you're doing exactly. Yes?
I have a question. Why do we need to use bootstrapping? I mean, if the sample size is big enough, we can get very accurate statistical inference. If the sample size cannot represent the population, we still use bootstrapping. But I think because the sample size is not very accurate, so the result of the bootstrapping will
Okay. Question was, why do we use the Bootstrap? When you have a big sample size, you often don't need it. When you have a big sample size, you often don't have to make many, if any, distributional assumptions about your data, which is nice because you can. Okay. You can appeal to asymptotic results, large sample results, and do just fine. When you have a small sample size, often you're stuck making a distributional assumption, like with a t-test. Small sample size, if you have 10 observations, you want to do a t-test, you have to assume that your data are normally distributed for the t-test to work. And checking whether the normal distribution holds with just 10 numbers is challenging. It's not really possible to do it. So if you had, say, small sample size and you didn't feel comfortable making a distributional assumption, Bootstrap's great right there. Even if you have a large sample size, sometimes there's not an easy off-the-shelf method for doing inference. So we'll see some more sophisticated types of data later, like survival data or correlated data. And the methods to do confidence intervals and p-values with more complicated data can get challenging and or non-existent. There may not be any analytical results that apply. Because you might have a very unusual type of inference you want to make. I want to do inference on the median of this variable minus a particular. I find it especially attractive when we have small sample sizes, and in more like custom applications where there's not off-the-shelf options. Not sure what's going on. Looks like they're recording again. Okay. All right. So to do a confidence interval, a Bootstrap-based confidence interval, this is an example. We sample with replacement, capital B times, and after doing that, we now have capital B versions of our statistic. We could make a histogram and look at them, and that's a rough picture of the sampling distribution of p hat. If you want a confidence interval, the way we can get a confidence interval is we need the sampling distribution of our statistic. So if we could draw this picture and say, on repeated sampling of 16 games, if you computed p hat, this is what you would see. Then what we are describing as a confidence interval can just be defined as the percentiles from this sampling distribution. And I'm carving out the 2.5th and 97.5th percentiles. If I do that, there's 2.5% to the left there, and there's 2.5% to the right over there, which means in the middle is 95%. 95% of the probability in this distribution is between those endpoints. And it turns out that if you do that, you get the interpretation that we want of a confidence interval. Namely, 95% of all intervals constructed like this can be expected to contain the true mean. So to do Bootstrap, we sample with replacement, and then a confidence interval is, give me the percentiles that correspond to the confidence level we want. If I wanted 95%, I get 2.5 and 97.5. If I wanted, say, 80%, I'd need to capture the inner 80%, which means 10% on either side. So I would need the 0.1 percentile and the 0.9 percentile. We did this simulation where we were able to make this picture over here. So remember this picture when it comes time to interpret a confidence interval. I can guarantee you I will ask you on your exams, tell me what a confidence interval means. Tell me what a p-value means. Interpret them. The way I would interpret a 95% confidence interval is, the most vague way is to say I'm 95% confident that p is inside my interval. Suppose we computed an interval from 0.4 up to 0.85. That's my 95% confidence interval. Being vague, I could say I'm 95% confident that p is in there. If pressed, what do you really mean by that? In particular, do you mean that the probability that p is inside that interval is the probability that p is between 0.4 and 0.85 equal to 0.95? And the answer to that is no, because now that we've computed the interval, there is no probability anymore. P is a fixed number. We don't know what it is, but it's a fixed number. And we now have an interval defined by two fixed numbers. So the truth is either in our interval or it is not. Once we have our data and we compute one of these things, we have no way of knowing whether ours captured the truth or not. All we can say about confidence intervals is 95% of these 95% confidence intervals will contain the truth. My particular one, I just can't tell you yes or no. So that's what this simulation was about. And I asked you to consider changing this desired confidence and run it a few times. 95% of all your 95% confidence intervals will contain the truth. If you changed this to 80%, 80% of those intervals would contain the truth. And remember the general trade-off. If you want more confidence, if you want to have higher confidence, you have to widen your interval. If you want a narrower interval to be a little more precise, you get less confidence because it's harder to get more precise. Okay, now let's talk about hypothesis tests using the Bootstrap. A confidence interval is one type of inference. It's a confidence statement about the population made on the basis of sample data. But it's an interval estimate, that's what it is. What if we want to make a formal decision? Yes or no, are they better than chance, this team? We're going to make a decision, yes or no, and we would like to be able to assign our level of confidence to our decision. I think they are a better than average team, and I'm 92% confident in that statement. We'd like to be able to say things like that. Okay, so what we might do, or what we always do in a hypothesis test is, for a hypothesis test, we formulate our problem in terms of two competing hypotheses. The null hypothesis is that the parameter of interest, whatever that is, takes a specific value. We always pick a value under the null hypothesis, even though sometimes it feels like you want to put in like a one-sided null or something. Because of the math, and we'll talk about it a little bit if we have time, you always have to pick a number for the null hypothesis. So I would say in this case, with the NFL data, my null, a natural null hypothesis to stick with as far as we know, is that they are an average team. And then my alternative hypothesis is something other than that. And there's different ways to do it. We could have one-sided or two-sided alternatives. Let me see what I have the script over here doing. Okay, we're going to do a one-sided alternative. We are going to consider for this team Are they average or are they above average? The null hypothesis is always one specific value. The alternative is an interval or a range, a collection of possible values. So we say, let's assume the null, and let's ask, if that were the case, if p is really 0.5, how likely would it be to see what we saw? And if that likelihood, which we call the p-value, if that's small, below some threshold, 0.05 say, we confidently reject the null. In which case we can say, you know, I'm 95% confident that they are an above average team. In this example, we could compute the p-value exactly, directly. Because we're just working with binomial data, this is the p-value. This command right here, p binom, is a cumulative probability. Like p binom of 8 here would be defined as the probability that this binomial random variable takes a value of 8 or less. It's a from the left accumulation of probabilities, also called a CDF, cumulative distribution function. What I have on the screen is 1 minus p binom of 8. The second argument is the number of trials that we're considering, and the third argument is the probability that we're considering as the probability of success. So p binom of 8 with 16 trials and 0.5 probability of success would be the probability of winning 8 or fewer games when p is 0.5. The p-value that I want is the probability of seeing 9 or even more. Because of the form of this alternative, I'm interested in right side relationships. I'm interested in evidence that p is bigger than the null value. So what I'm going to want to compute is probability that I would see 9 or even more under this case when the null is true. That's what this does. 1 minus the probability of 8 or less is the probability of not 8 or less. That would be the probability of 9 or 10 or ... up to 16. This is going to be same thing as this 0.4 that we got. The 0.4, the first 2 0.4s there, 0.401617, those are simulation based. I didn't actually compute the probability directly. I simulated a big pile of realizations, and then I computed a proportion of those simulations. It's the same idea. That's why this number is so close. They're doing the same thing. If you can write down the distribution, you can always do calculations from it. Otherwise, often, you can use your computer to do simulations, and it's just as good. It's just like you knew the actual distribution. Okay, now I want to show you how to do the same thing, but using the Bootstrap. So let's come down. Yeah, let's come down here. We already have a confidence interval. Now let's get a p-value. To do Bootstrap hypothesis testing, I'm going to increase this to 1,000 again. To do Bootstrap hypothesis testing, it's still Bootstrap, which means the essence is, again, sample with replacement, and then recompute your statistic. So that's simple, but the extra detail when we want to do a hypothesis test is that we don't just want the sampling distribution of p hat. For the p-value, we specifically want the sampling distribution of p hat under the restriction that the null hypothesis is true. A p-value is probability of our data, or even more extreme, when the null is true. So if we're going to use the Bootstrap, all it does is resample with replacement to mimic a sampling distribution. I want to do that, but I specifically want to do it when the null is true. So what we do is, before sampling with replacement, we transform our data to make it as though the null hypothesis is true. What that means in this context, 16 zeros and ones, and my null hypothesis is that p is 0.5, what I need to do is modify my zeros and ones to make it so that the proportion is 0.5. If I transform my data so that the null hypothesized value holds, it turns out then we can sample with replacement from that. If I do this highlighted piece, Texans 2015_0, by that I mean the Texans 2015 data under the null, is the original zeros and ones minus the mean of those zeros and ones plus 0.5. So see what happens when I did that. I need to define this. So the mean of the original data was that 9 out of 16. The mean of a bunch of zeros and ones is the same thing as the proportion, right? If you add up the ones and divide by the total number, it's the same thing as a sample average. Having done this transformation, we have that the null hypothesis is true for this transformed version. It's a little bit weird in this case because our numbers are not zeros and ones anymore, but it still works. Okay, and we're going to apply this to continuous data soon in the same exact way. The main thing is if you're going to do Bootstrap testing, you have to modify your data to force the null hypothesis to be true, and then you apply the Bootstrap. That's what I've done down here. Where did it go? Okay, here. Now let's do the resampling. So Texans 2015-0, ready to go. And I'm going to have this loop. Each time I'm sampling with replacement from the null transformed version of my data and computing p hat each time. So let's run this. Now we have 1,000 versions of our p hats. And these were computed under the null. So this is an approximation of the sampling distribution of p hat under the null, which means that the p-value in the context of the NFL data, the p-value will equal the probability under the null hypothesis that y is bigger than or equal to 9. That's the same thing as the probability under the null hypothesis that p hat is bigger than or equal to 9 over 16. And what we just did over there in R was get the sampling distribution of p hat under the null, which means we can compute that by just doing the proportion of our 1,000 simulated or bootstrap p hats that are bigger than or equal to 9 over 16. P-value. The mean there could equivalently be written this way. P-value is the sum. How many of my bootstrap p-hats were bigger than or equal to the original observed one, and then divide by the number of bootstraps. They will give us the same number. .43. So that's really kind of neat, I think, because we matched the same basic p-value, 0.4-ish, 3 different ways. One, we computed it via simulating from the binomial distribution. 2, we computed it exactly using the binomial CDF. If you've ever heard of like the Fisher's exact test, those types of things, those are exact calculations, exact tests. We kind of did an exact test here. And we did it via the bootstrap. And that was the most general that we did. When we did the bootstrap, there was no mention of binom or anything in there. We just sampled with replacement. What's that? In the simulation, we did specify the distribution in this case because we simulated directly from the binomial. That's perfectly fine in this case because it is binomial. But you know, if you have other types of data like time course data or something, you don't have a built-in distribution function necessarily. All right, so that's a p-value. Let me show you another simulation here. In this script, I showed you how to do confidence intervals with the bootstrap. And I also did a simulation that illustrates what confidence intervals are. So we had that picture of all the green and red line segments. Now I've shown you how to do a test with the bootstrap, and now I'm going to do a simulation to illustrate a little bit further. So what follows in the remaining here is a simulation. Simulations are very valuable. One of the reasons I like to push people to learn a little bit of R in this class is that there's often times that you don't know or have the ability to answer a particular question. For example, sample size calculations. Maybe you in your laboratory are doing research on mice and you have a particular treatment that you're interested in and you want to compare it to some other control treatment. Suppose that you expect your drug to have a 20% increase in the lifetime of the mice or something. You expect there to be a particular effect size, 20% extra over the average otherwise. And suppose you plan to test at a significance level, a type 1 error rate of 0.05. I'm only going to reject the null if my p-value is less than 0.05. And suppose that 20% that you're hoping your drug will attain, you want a stated level of power, statistical power, to detect it. So suppose I'm going to test at significance level 0.05, and I want 80% power. I'll say something more about power in just a moment. But I want high likelihood of actually detecting. If it really is 20% or more, I want 80% probability of detecting it. If you wrote all those things down, the only question left would be, how many mice do you need to get? testing at significance level 0.05, you want to detect an effect of such and such size. What does the sample size need to be in order to give you the 80% power that you want? There are books full of sample size calculation formulas, you know. But you can always approximate those formulas with a short little simulation in R or in any programming language. So imagine if you just simulated a big sample, a huge number of simulations of sample size 10. Under the scenario that you're going to be experimenting under, postulate some values for like the averages and the variances in the population, and let n be equal to 10. Simulate a whole bunch of times. How frequently did you detect a 20% difference when it was really there? Then change n to 15 and 20 and compute via simulation an approximate power by sample size, and then pick the sample size that gave you a simulated power of what you wanted. Pick the smallest sample size that got you above the 80%. You could use simulation to answer that. You can use simulation to do things like, okay, I have 10 observations on those mice, but I also have 3 technical replicates of each one. Should I average those technical replicates? Or should I include them all in there as if they're all independent draws? You can do simulations to investigate just about anything. If you can figure out how to code it to mimic your scenario, you just simulate lots of times. And then you can learn about operating characteristics by inspecting the simulations. I'll give you some opportunities to play doing simulations this semester. Here's one. I'm going to simulate 1,000 times, and we're going to initially say that the null hypothesis is true. The probability of winning a game is 0.5. I'm going to do inference at 80% confidence. We could change that to 90, 95%. What this means when I say desired confidence is that my significance level, what you might call alpha in Stats 101, is 1 minus that, 0.2. So let's change it to 0.95. That's a more standard choice. 0.95 is my desired confidence, which means I'm going to test at significance level 0.05. That means if the p-value is less than 0.05, that's when I'm going to reject. Otherwise, I won't. This simulation, inside, we're going to simulate a single 16-game season, just like the one that we have at the very beginning. Let p be equal to 0.5, and let's simulate a 16-game season under that scenario. Let's do that and compute p hat every time. And then let's use the Bootstrap to compute a p-value. So up above, earlier when we did a simulation, we did multiple loops, and inside each one of them, we did the whole thing. Sample from the population and do Bootstrap to get a confidence interval. And then we could look at, okay, here's our 1,000 confidence intervals. We could see what confidence intervals do. Now we're going to do the same thing, except we're going to, inside the loop, simulate a data set, and then use the Bootstrap to get a p-value. So now we're going to have 1,000 p-values simulated. I'm setting up for the Bootstrap by transforming the data, just like we did above. I'm going to subtract the mean to make the mean 0, and then I'm going to add back what I want the mean to be under the null. And then I'm ready for Bootstrap. Sample with replacement, and compute the statistic each time. My p-value would be the proportion of simulated or bootstrap p-hats that are as big or bigger than the one we originally observed for our simulated data inside this iteration. For the current simulated data set, what proportion of the bootstrap p-values or p-hats were bigger than or equal to our observed ones? So we're computing a p-value every single simulation, 1,000 times. And every time we do this, p is equal to 0.5. The null hypothesis is true. If you do a hypothesis test at significance level 0.05, what you're doing is you're saying, I'm guarding myself against making a particular type of error, a type 1 error. By restricting your p-value to be less than, say, 0.05, what that translates to is the probability that if the null really is true, you will incorrectly reject it no more than 5% of the time. We're going to make type 1 errors with probability 0.05. This simulation-based one came up at 0.035. Here's another one, 0.033. The bootstrap is a little bit conservative. We're actually making type 1 errors less frequently than that 0.05, just a little bit. Let me make this last picture and we'll be done. What I'm going to do now is, instead of simulating when p is 0.5, let's simulate for a variety of p values. Let me go ahead and run this because it's going to take a minute probably. This simulation is repeating what we just did, but instead of letting p be a single number, see this p-seq? I'm considering a partition of p-values, probabilities. So 0.01, and then 0.03, and then 0.05, dot, 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 all the way up to 0.99. For every single one of those, we're going to treat that as the truth and do a simulation. So at the end of this is going to take a little while. I'll have to show you this next time because this is going to take a while. What we're going to see is a picture like this. Here's true value of p. Here is rejection probability. The probability that under these different choices of p, you would reject the null. When p is equal to 0.5, the null hypothesis is true. The probability of rejecting the null incorrectly when the null is true is the significance level, 0.05. So what we're going to get in this picture when it finishes running is like an S-shaped curve, where this is at 1, this is at 0. This is called a power curve. Power is probability that you reject the null hypothesis when you're supposed to, when you should. You should not reject it if p is 0.5, but anywhere out this way, you should reject the null because it's not true. As p gets further and further away from the null, it gets easier and easier to tell. That's why the S curve is going up and up and up towards 1. Okay, it's called a power curve. Big picture today is still using Bootstrap. Now we know how to do confidence intervals and hypothesis tests. Next week, I'll review t-tests and relate them to the Bootstrap, see how they work as the same thing. And then we'll talk about Bayesian inference. 3 different ways to do statistical inference. Questions right now? Okay, have a good weekend.